Hey guys, here we're going to continue our polynomial division lesson. In the previous video, we divided polynomials using long division. Now we're going to look at how to divide polynomials using something called synthetic division. Now, synthetic division is actually really nice. It's a bit easier to do than long division. However, it only works when you are dividing by a linear factor. Now, what that means is if what you're dividing by, which is the x minus 3, is linear. And when something is linear, that means that the highest exponent of x is just 1, which is exactly what we see here, because even though we don't see an exponent, that's kind of like an imaginary 1 there. So, or rather, invisible 1. So what we do first is we take what we are dividing by, which is the x minus 3, and we make it equal to 0. And then we solve for x. In this case, x is equal to 3, since we would have to add the 3 over to the other side. Now this is this is how we set it up. What we do is we open a little box here on the left side and we put that number. Then over here going across, we're going to write the coefficients of the polynomial. So 6, negative 25, 18, and 9. Then you always bring down the first term, or the first coefficient. Now you're just going to follow the same pattern. You're going to, whatever number is down here, you're going to multiply it with the number that's in the box. So 6 times 3 is 18, and we write it right underneath here. Then you combine. Negative 25 plus 18 is negative 7. Now we repeat. Negative 7 times 3 is negative 21. Combine again. 18 minus 21 is negative 3. Multiply. Negative 3 times 3 is negative 9. And then finally combine again. 9 minus 9 is 0. This last number here, this is the remainder. In this case, we have no remainder. These numbers here represent the coefficients of the quotient, meaning the answer to the division problem. Since we are dividing by a linear factor, when your answer will always be 1 degree less than the original polynomial. So since the degree of this polynomial is 3, 1 degree less would be 2. So that would be the variable's exponent of the 6. So this would start as 6 x squared, and then everything else goes in decreasing order. So negative 7x, and then the negative 3 is the constant. And this is our answer. So this is called the answer to a synthetic division problem. This is called a depressed polynomial. Depressed because, we took away a degree, so it is smaller. And when you think of depression, it's smaller. Let's look at some other examples. Here we have 7x to the third minus 6x plus 9 divided by x plus 5. And I put here in blue, just like with polynomial long division, if you are missing a term, make sure to use 0 as a placeholder. So first, let's figure out what we're going to put in this little box. And that's always when we take this linear factor and we make it equal to 0 and solve for x. In this case, we would have to subtract the 5. So if you do that, you get that x is equal to negative 5. So that's the number that I put in the box here, negative 5. Then going across, we put the coefficients. So we start with 7. Now, as I wrote here in blue, we are missing the x squared term. So if we're missing a term, we put a 0 for where that term would be. Then it continues to negative 6 and 9. Bring down the first term, which is 7. 7 times negative 5 is negative 35. Zero minus 35 is negative 35. Multiply again. Negative 35 times 5 is 175. Negative 6 plus 175 is 169. 169 times negative 5 is negative 845. And 9 minus 845 is negative 836. So this is my remainder. Now, just like with polynomial long division, you always put the remainder over what you divided by. So this is how you would write your final answer. My highest exponent here for the polynomial that we were dividing is 3. That means that my exponent here would start with 2. So this is 7x squared minus 35x plus 169, and then we add the remainder, which in this case is negative, so minus 836, and we put it over what we just divided by, which is the x plus 5. And this would be my final answer. Now here we have 4x to the fourth minus 3x squared plus 7x plus 2, and we are dividing by 2x minus 1. First of all, let's take note that we are missing the x cubed term that's in between. So in between here, I would put a 0x cubed when we are writing our coefficients. In order to figure out what number is going to go in the box, we need to make this linear factor equal to 0. In this case, I would have to add the 1, so 2x is equal to 1, and then you divide the 2. Which would give us that x is equal to 1/2. We write our coefficients going across. We have the 4, 0, negative 3, 7, and 2. Bring down the first term. Now here you're probably freaking out because what's in the box here is a fraction, which whenever you have a fraction, just keep in mind that fractions are simply division. So instead of thinking of 4 times 1/2, you can also think about it as 4 divided by 2. So because that's what 1/2 represents, it's division. So 4 divided by 2 is 2. 0 plus 2 is 2. 2 divided by 2 is 1. Negative 3 plus 1 is negative 2. Negative 2 divided by 2 is negative 1. 7 minus 1 is 6. 6 divided by 2 is 3. And 2 plus 3 is 5. So this is my remainder. So now when we're writing our answer, our highest exponent here for the polynomial is 4. That means that our exponent for the quotient is going to start with 3. So this 4 is 4x to the third, and now we go in decreasing order. So plus 2x squared minus 2x plus 6, add the remainder, and put it over what we just divided by, which is the 2x minus 1. And this would be our final answer. Now, let's look at the remainder theorem. Now, what the remainder theorem states is that if you were trying to find a function value, that means that the remainder would actually be that function value. So it's best to explain it using an example. So I have here f of x is equal to x to the third minus 4x squared plus 5x plus 3. If you were trying to find f of 2, what we would normally do is plug in 2 for every x and evaluate. Now, the remainder theorem states that you don't have to do that. Instead, this number here, this is the number that we would put in the box. We put our coefficients going across, so 1, negative 4, 5, and 3, since we're not missing any terms here. Bring down the 1. 1 times 2 is 2. Negative 4 plus 2 is negative 2. Negative 2 times 2 is negative 4. 5 minus 4 is 1. 1 times 2 is 2, and 3 plus 2 is 5. This is my remainder. So what the remainder theorem states is that your function value, the one that you are trying to evaluate for, is going to equal to the remainder. So if I were to plug in 2 for every x, my answer should end up being 5. And just so you can not take my word for it and see how that actually works out, let's go ahead and find f of 2 using regular substitution. So f of 2 would equal to 2 to the third minus 4 times 2 squared plus 5 times 2 plus 3. 2 to the third is 8 minus 2 squared, remember you always do the exponents first, 2 squared is 4 times this 4 is 16 plus 5 times 2 is 10 plus 3. Now 8 minus 16 is negative 8. Negative 8 plus 10 is 2. And 2 plus 3 is 5. So you see how you get the same thing. So this is regular substitution. And here we use synthetic division in order to find that function value, which is why the remainder theorem is also called synthetic substitution. So that's what that means. The remainder is equal to the function value that you are trying to find. Now let's look at the other theorem, which is the factor theorem. Now the factor theorem states that if you are given a factor and you are trying to test to see if this is a factor of the polynomial, meaning that would we be able to continue factoring this polynomial given the one that we're testing. If it is a factor, that means that we would end up with 0 as the remainder. If you don't end up with 0, then x plus 4 or x minus 1, whichever one you're testing, would not be considered a factor of the polynomial. So let's test that out. Here, if we have x plus 4 and we make it equal to 0, we would have to subtract the 4, so x would equal to negative 4. So that's the number I'm going to put in my box. We put our coefficients. We're not missing any terms, so we would just write 2, 8, 2, and negative 12. Bring down the 2. 2 times negative 4 is negative 8. 8 minus 8 is 0. 0 times negative 4 is 0. 2 plus 0 is 2. 2 times negative 4 is negative 8. And we end up with a remainder of negative 20. So that means that x plus 4 is not a factor of this particular polynomial. Now here let's try x minus 1. If we make this equal to 0, we would have to add the 1, so x would equal to 1. So that's what I'm going to put in my box here. And we write our coefficients, so 2, 8, 2, and negative 12. Bring down the 2. 2 times 1 is 2. 8 plus 2 is 10. Times 1 is 10. 2 plus 10 is 12. 12 times 1 is 12. And we end up with a remainder of 0. So that means that x minus 1 is a factor of the polynomial. Now, if I want to completely factor the polynomial, we would have to then rewrite this as the depressed polynomial. Since my highest exponent was to the third, that means that this highest exponent would be squared. So f of x, my polynomial, is equal to, now we tested x minus 1 is a factor, so we have to include that in our answer. So I like to write it first just to remember that, not to forget it. Then this here, this represents 2x squared plus 10x plus 12. And now we want to continue factoring this polynomial. If you look at this quadratic, every single term is divisible by 2. So that is my greatest common factor. So I'm going to take out a 2 from that quadratic. So I'm going to write the 2 in the front. I have the x minus 1. And since I took out 2, that leaves me with x squared plus 5x plus 6. Then this is just a regular quadratic that we can factor. The two numbers that multiply to give you 6 and add to give you 5 are 2 and 3. So my factors would be 2, x minus 1, x plus 2, and x plus 3. And this is my polynomial in completely factored form. So that is the point of the factor theorem, is if you're given a factor, you want to be able to divide it, so that way you end up with something that you can factor, and you can completely factor that polynomial. Let's try that one more time. Here we are given x to the third plus 3x squared minus 4x minus 12. And we want to determine whether x plus 3 is a factor of this polynomial. And if it is, we want to be able to completely factor the polynomial. So let's try this out. If we make this factor equal to 0, then we would have to subtract the 3, so x is equal to negative 3. So that's what I'm going to put in my little box. Then rewrite these coefficients going across, so 1, 3, negative 4, and negative 12. Bring down the 1. 1 times negative 3 is negative 3. 3 minus 3 is 0. 0 times negative 3 is 0. Negative 4 plus 0 is negative 4. Negative 4 times negative 3 is 12, and we end up with a remainder of 0. So that means that x plus 3 is a factor of the polynomial. So let's write out our polynomial so far. We have the factor that we tested that is a factor, so we're going to include that in our polynomial answer. Then because this highest exponent is to the third, that means that here we're going to start with x squared. We have no x, that's why there's a 0, so please don't write the 0x. And then we have minus 4, which is the constant. Now this x squared minus 4, this is a difference of squares, since x squared is a perfect square and 4 is a perfect square. So remember, when you factor, you square root the first term. The square root of x squared is x. The square root of 4 is 2. Make one factor positive and one factor negative. And this is my polynomial now in completely factored form. Let's look at this last one here. We have x to the fourth minus 4x to the third minus 6x squared plus 4x plus 5. And we want to divide by x plus 1 to check if it is indeed a factor. So first we make the factor equal to 0. In order to solve for x, we would have to subtract the 1, so x is equal to negative 1. So that's what I'm going to put in the little box. We write our coefficients. We're not missing any terms. So 1, negative 4, negative 6, 4, and 5. Bring down the 1. 1 times negative 1 is negative 1. Negative 4 minus 1 is negative 5. Negative 5 times negative 1 is 5. Negative 6 plus 5 is negative 1. Negative 1 times negative 1 is 1. 4 plus 1 is 5. 5 times negative 1 is negative 5. And 5 minus 5 is 0. So that means that x plus 1 is indeed a factor of my polynomial. So g of x so far, we have the factor that we tested, which is x plus 1. Since my highest exponent here was to the fourth, that means that this is going to start to the third. So we have x to the third minus 5x squared minus x plus 5. Now here we have 4 terms. And if you ever have 4 terms, you're going to factor this by grouping. So we group the first 2 together and the second 2 together. So let's factor that. We have the x plus 1 already on the outside. X cubed minus 5x squared has the greatest common factor of x squared. And if I take out the x squared, I'm left with x minus 5. Over here, we have negative x plus 5, keeping in mind that we want what's in the parentheses to be the same. We want it to be positive x minus 5. So here we have negative x plus 5. Those signs switched. So what we're going to factor out is a negative 1 to switch those signs, which would give me positive x minus 5. Now what I have here inside the parentheses is the same. So we're ready to continue. We have the x plus 1 on the outside, the factor that is inside the parentheses, and then remember what is left over outside the parentheses is our other factor, which is x squared minus 1. Now this x squared minus 1 is another difference of squares. So when we factor, We have this x plus 1 here. We have the x minus 5. Remember factoring a difference of squares? We're going to square root the first term, which is x. Square root the second term, the square root of 1, is just 1 again. Make 1 plus and 1 minus. So we have x plus 1, x minus 5, x plus 1 again, and x minus 1. So this is our polynomial. But if we want to write this a little bit more concisely, since we have two x plus 1's, we can write x plus 1 squared, because there's two of them, x minus 5, x minus 1. And this is my polynomial in completely factored form. And that's synthetic division, the remainder theorem, and the factor theorem.